Yeah, hello and welcome to the lecture on Browian motion. So usually, Browian motion is serves as some mathematical model for a variety of random phenomena observed in the natural and social sciences, including erratic motion of microscopic particles suspended in fluid, right? The evolution of stock prices in financial markets and the diffusion of heat or pollutants. Actually, historically, I can say the first person who observed Brownell motion or who brought about this Brownell motion in 1827 was Norbert, that's Robert Brown, a botanist. He noticed the movement of pollen grains suspended in some water. Okay, so that was how he realized that, oh, so if the movement of these actually can actually serve as like the application in physics. Yeah, so in his garden, this is what he noticed. But later on, this man was the first to model the movement of stock prices. That's Louis Bachelard. So he was the first person to model stock prices. You see, because of that movement of the pollen grains suspended in the water, they've been able to several like modifications have been made to this observation made by Robert Brown. Such that this man in 1900 realized that no, the movement of stock prices, okay, can be modeled by this same Brownian motion, right? So the physical explanation was given by our genius later on. That's in 1905, 5 years later. That's Albert Einstein. Yes, so he modeled several collisions with the fluid molecules, right? Yeah, so Norbert Warner was the one in 1931 who came out with the final mathematical foundation of Brownian motion, right? Norbert Wiener. Yes, so when you hear the Brownian motion of the Wiener or the Wiener process, is the same thing we are talking about. The Wiener process, or he actually brought the mathematical foundation of the Brownian motion, what Robert Brown observed. So this diagram just showed the movement of the fluids suspended in the fluid, like we spoke about, right? And then the phenomenon shares the same behavior as the stochastic Wiener process used by mathematicians, like what Robert Wiener used, right? Yes, so the Brownian motion actually can be viewed as the physical or the mathematical version of the Wiener process. That is one thing you can notice about it. So they're the same, just that one is the mathematical version. So the Wiener process is the mathematical version of the Brownian motion, right? So these concepts are foundational in modeling uncertainty and randomness in various fields, right? Yeah, so human behavior is uncertain. It moves in any random order, can be modeled as a Brownian motion, right? Good. So before that, we have to look at, so we want a concept like the random walk to extend to that of our Brownian motion. That is where our basis will begin from. So to construct a Brownian motion, we begin with a symmetric random walk. Symmetric in the sense that, so we know how the drunkard walks, right? So symmetric random walk, or maybe the drunkard walk. So we're saying that the drunkard, we know, moves in a random manner, either forward or backward movement or something, right? So we are saying that it's a symmetric random walk because the probability of moving forward and backward is the same. That's why we make it symmetric. We all know how the symmetric wasn't it? The normal distribution is symmetric because it's divided into two equal halves, one at the positive and the other one at the negative side, right? Good. So symmetric random walk. So we're saying that you can even look at it. We are going to look at it purposely from the side of the drunkard walk, like steps taken, right? Yeah, but you can also look at it like tossing the coin to get either a head with probability p and a tail with probability 1 minus p, each giving us 1 over 2. That's symmetric because the flips give us equal chances of probabilities, right? So a random walk is a mathematical formulation of a trajectory that consists of taking successive random steps at every point in time. So now this can be seen as a graphical representation of a random walk. So we say that in every walk you take, you either have a +1. So initially, when you don't make any walk, you are the initial stages, that's the origin. When you make a step upward, so this one m1 means that's the first step upward, and we know the steps are cumulative, so your current location are like the m's. So the first step is m1, And this person actually, so the person made a step forward and came back to the origin again. You realize, so move backward like -1. Every backward movement is -1, and the forward movement is a +1 step, right? That's why I said we are looking at the aspect of the drunkard walking or moving either forward or backward. Yeah, so that is how these M's denote. So from here, the drunkard moved backward again. You see that the steps are becoming negative. That's -2. If we move up again, you see we make that's +1. We get to -1. If you move upward again, we get to M6, and that will be a 0 again. We move top, we get to 1. That's +1 step. Now that's our current location. Okay. Yes. So let's look at the symmetric random walk in the details. I think I've explained all these randomness or symmetricness in the flips, right? So I'm saying that Zi is giving us 1 or -1 if the flip is a head, and -1 if the flip is a tail. So we can also look at it as a +1 step if the drunkard moves forward, and a -1 step if the drunkard moves backward. So let's proceed. So we are saying that what will be our current stage, like where we are right now, is the M's. Remember I told you. So the M's looks at the summation of all our steps to the current location. So MK is the kth step. So our kth step is giving us what? The summation of the individual steps. Remember, each individual step is the Zi's, and I could either be 1 or -1. So we have to sum all these up to get our MK, which is our kth step. So it's a symmetric random walk to approximate a wiener process in a continuous time setting for n belonging to positive integers. We define the scale symmetric random walk as this. So now, pay attention here. We are trying to say that this is a symmetric random walk, but we will want to approximate this to the continuous setting, and to do that, it will send us to the continuous domain. Remember, these are discrete steps you are taking. So to send it to the continuous domain, then it becomes a wiener process, right? And the concept is that we are scaling the symmetric random walk to that of the continuous domain using the Donski's theorem. So this symmetric random, we're saying that WT, what will be WT? WT should be equal to the scale symmetric random walk, which will be 1/√n, then M, the floor. Remember, these are discrete steps, so we are taking time times the number of steps. So this may give us integer values, or maybe it will give us real numbers. So we are trying to say that whatever value it gives you, we want the floor of it. As in, if you get 2.99 or 2 point whatever, you are going to approximate to 2 steps, right? Yes. So that's the floor of it, so that we still have that discretization in it, right? Good. So we all know that MK will give us what? Summation as I run from 1 to k of Zi. So this is MNT, the floor. So it means that we need to sum from I run from 1 to NT, the floor of that, right? Good. So such that the limit as n approaches infinity of this wiener process will make us move from the discrete domain, because n is the number of steps. So if the limit exists, this n will vanish, leaving us with only t, WT, where WT is going to be normally distributed with a mean 0 and a variance t, right? Good. This is known as the Donski's theorem. So now, what we want to do is to prove the Donski's theorem. But before we do that, let's look at the symmetric random walk as a martingale. We know that MT should be equal to this expression because k is now replaced by t. So we know M0 initial stage should be equal to this. That's fine. Should be 0. Then probability that Zi is equal to 1 and that of -1 should be symmetric. That's 1/2. Right. So if you have any j less than k, for all these j and k being positive integers, we want to show that mk given fj should be equal to this, which we know that is a martingale if the proof appears to be positive. Right. So all we need to do is to create within the process mk. So we introduce j. Yeah. So this is create and undo. That's do and undo. Sure. So we add that, we get 0. So this we are going to take expected value of mj given fj, which will give us mj, plus the expected value of mk minus mj. All right. So this one, remember we are saying that by independence, so by independence, you realize that when we look at fj looks at the process from time 0 to j, and that of mk minus mj looks at the process between time j and that of k. So these two intervals do not overlap. You see this from here and from here to that other side, they do not overlap. So because of that independence, it means that mk minus mj is independent of fj. So as such, we are going to get the expected value over here to be what? Expected value of mk minus mj, right? Yes. So plus mj, because this natural filtration is going to give us this. Recall the expected value of mk minus mj is equal to 0 because because the expected value of zi should be equal to what? That's the random variable times the probability, and that will give us 0. So if you want to find the expected value of mk, it should be equal to the summation of what? This is a linear operator. Summation is a linear operator. All right, it's a linear operator, so that will give us 0 as well, because once this is a linear operator, we're going to get expected value of zi summation as I run from 1 to k. All right, but expected value of zi is already 0, as we can see here. So as summing 0, even k time will still give us what? 0. So remember, expected value is a linear operator, so this is the same as expected value of mk minus expected value of mj, which are all 0. So that will give us 0. Yeah, so everything will now be left with expected value of mk given fj to be equal to mj, and that is just that. So now let's proceed to prove the Donski's theorem. We know this already. The Donski's theorem from the symmetric random walk, the scale symmetric random walk, is this, right? So all we need to do is, we say from the Donski's theorem, the mean is 0 and the variance is t. Let's prove that. So to find the expected value, all right, let's move to the next slide and prove that. So we find the expected value of the wiener process, or the scale symmetric random walk. Yet note that the expected value of zi should be 0. We know that, and the variance should be equal to 1, because from here, if you find, I'm coming, yeah, so if you want to find the second moment here, that would be 1 squared times half plus negative 1 squared, which is 1 times half. That everything will give you 1. Second moment will be 1. The variance will be the second moment minus the mean squared. The mean is already 0, so that gives us the variance to be 1 as well, right? Good. And remember, the zi and that of zj are independent, right? Good. So the expected value of the scale symmetric random walk should be equal to this. So once expected value is a linear operator, the random variable is zi, so it can go inside. Once it goes inside, we know that expected value of zi is 0. So summing 0 and t times will give us 0. So that is that. Let's look at the variance of w t n, right? That's the scale symmetric random walk. Now the variance should be equal to the second moment minus the square of the first moment. But remember, the first moment, which is 0, we'll just equate our variance to that of our second moment, meaning our second moment is the same as the variance. So what do? We move forward. So it's by squaring everything. So we're squaring the scale symmetric random walk. That is by squaring everything here. Okay, so when we square this, we're going to get 1 square will give us 1, and root n square will give us n. When we square that of zi, we get zi squared, and when we strike expected value true, remember the only random variable is going to be the zi, so that will be expected value of zi squared, which you know to be 1, or you can even say the second moment is the same as the variance right now, so that's variance of zi. Okay, and variance of zi we all know to be 1. So summing a constant nt times is going to give us nt, right? A constant 1 nt times is going to give us nt, and this is just a floor, so we're just using this notation to show that it's a floor that we are taking. So now just give a nt over n, and that will give us t. So it means that we've proven and showed that the Donskis theorem is actually true. The variance is t, and out of the mean to be 0, okay, following the normal distribution. So now we all know as n approaches infinity, the expected value is there. That's from the central limit theorem, and then the variance is also going to give us t. Now from the central limit theorem, as I said, we conclude that the limit as n approaches infinity of the scale symmetric quantum walk will leave us without the n, okay, giving us only wt, which we call the wiener process, being normally distributed with a mean 0 and a variance t. So yeah, I think I've concluded on this. So this is the same as wt, yeah, and it is also known as the Browian motion, right? So now let's give a standard definition to the Browian motion. So assuming we have a probability space, a stochastic process bt, where bt is called the standard Browian motion or wiener process, like I said. So I'm saying that b0 is equal to 0, that's the initial stage, the process is equal to 0, and bt has continuous sample paths. So for each t, positive time t and s, the increment, that's bt minus bs, should also be another Browian motion with a mean 0 and a variance t minus s. This condition is what we call the stationary increment. For the independent increment, I was trying to say that if we have independent intervals, then the Browian motion should operate on independent increment basis, right? Just realize that if I draw a timeline here, so realize that if I have a timeline here, like I've drawn here, so looking at the process bt plus s minus bt, it looks like the Browian motion between these two time intervals. And if I take bt, for instance, bt looks at the process from time 0 to that of t, right? You look at it clearly, this means that this interval 0 to t is independent of that of the interval t to t plus s, because one of the intervals over here is not close at t, but one is close at t, so they are independent intervals. So in that case, the Browian motion has independent increments, right? Great. So let's look at the Browian motion in general with drift, right? So we say that a Browian motion with drift is generalized version of the standard Browian motion. It needs not to start at b naught is equal to 0 and may have non-zero drift. That is, the mu should be equal to what? Should not be equal to 0. Like the expected value of the Browian motion should not necessarily be equal to 0. That is a Browian motion with drift. And the variance not necessarily equal to t. So we can have a Browian motion like that. But those we are looking at is a non-drift Browian motion, the Browian motion with the non-drift term, right? So a process bt is called a Browian motion with drift if it can be written as bt is equal to mu t plus sigma wt, where wt is the wiener process, right? Yeah, so mu and sigma are all real numbers, and wt is the standard Browian motion, like I said. So now, after this Browian motion was introduced, a lot of modifications were made to it, right? A lot of modifications were made to it. So the first one was the reflection. Somebody says that, okay, sure. So this Browian motion that we've been talking about, what if we make it, we negate it? Is it also going to be a Browian motion? That's a claim. So let's try to see if that will be true. So now, to know that, we need to take the initial, that's b, r naught should be equal to negative b naught, right? Because they said rt should be equal to negative bt. So as we see, this is like negative 1 times b naught, which you know to be 0. So it means that the first condition is satisfied. So let's look at I think stationary increments, right? rt plus s minus rt. Let's see. So as we look at the negation side, this will give us this, right? Because negative bt plus s, then negative get positive bt. All right. So you realize that bringing this negation out, bt plus s minus bt, this is what we saw from the increment, the stationary increment cases, right? And we know that this has a mean of 0 and a variance of s. So it means this is very okay, stationary increment. So let's look at independent increment. So by independent increment, we need to see if the covariance is actually equal to 0. So for two random variables to be independent, it means that their covariance will be equal to 0, right? Good. That's okay. Let's proceed. So that is one thing you need to know about it. So expected value, and by covariance you realize that we want to find the expected value of the product, because covariance in general, let me write this down for you. Yeah, so if you recall the covariance of a function, let's say we have two random variables x and y. The covariance is given by the expected value of the product of x and y minus the product of the individual expected values. Alright, so in the context of Browian motion under the normal reflection, so you realize that because the expected value of these independent processes, Browian motions, because they are independent and have zero means, the product of the individual expected values goes to zero. So we are only left with the expected value of the product, which is the same as the covariance between the two Browian motions. Okay, and then looking at it clearly, you could see that this expected value will give us the product of that's bt plus s minus bt times bt, and by expansion we realize that this gives us 0. All right, so this is just for the stationary increment. All right, we've looked at that, and then this is for independence, and we've also looked at the first condition where r0 should be 0. So we can see clearly from all the three conditions of the Browian motion that under reflection, RT is also a standard Browian motion. All right, great. So the next to look at is the normal scaling. Like I told you, after Robert Brown and that of the Wiener, they came about this mathematical formulation of the Browian motion. Several other mathematicians wanted to look at maybe other formulations of this same Browian motion to see if they can use it in several applications. So that one of them is the normal scaling. All right, so let's say on a defined probability space, as we've seen before, the standard Browian motion, which is dt, we are going to define a new process which is nt, which will be equal to a real constant c multiplied by the time driven factor, that is t over c squared. So we want to show that this process nt is also a standard Browian motion, and as we all know, we are going to follow all those three conditions for the Browian motion. So first of all, we need to verify that n0 should be equal to 0, and by seeing and verifying, you realize that for t equal to 0, we have n0 as cb 0 over c squared will give us 0. That's indirectly b0, c times b0, which is 0, will give us 0. So first condition satisfied. So let's look at the second one, that is stationary increments. So we want to look at the idea that nt plus s minus nt given any chosen time spaces s and t on this boundary condition. So putting this into the definition of nt, we can express it as this. Then by stationarity, we know that this process should be normally distributed with a mean of 0 and the variance being the time difference, and this time difference is going to give us s. All right, so let's get the expected value. So by looking at this, we realize that because expectation is a linear operator, we can distribute it across these two different time domains, and by doing so we get 0 mean for the two. Multiplying it by the constant c does not make any difference, so that still becomes the same. So the next is to look at the variance of nt plus s minus nt. Okay, so this can be seen as the second moment minus the square of the first moment. But remember, the first moment has been proven to be 0, so it means that our variance becomes the same as the second moment. All right, so squaring this, we get this expression, and you can see that c squared is common, so we'll pull it out, and then we will be remained with these two nice expressions. Okay, once again, once the expectation is a linear operator, we strike it through. Yes, so because BT is a mean zero process, it means that the variance becomes the same as the second moment. So meaning this second moment can be seen as the variance as we move forward to the next slide. Okay, yeah, so this can also be seen as the variance of BT on c squared. Okay, then the expected value, we can pull 2 out as a constant, expected value of this product. Okay, because the individual means are 0 for these two processes, we can say that the covariance between BT plus S on c squared and BT on c squared is the same as the product of this expectation. Okay, yes. So looking at it, like I said, this is the variance, this is also a variance, and this can be seen as a covariance. So c squared has been pulled out, as you can see here, and we know that for a Browian motion, the variance of the process is actually the time. So that would be t plus s on c squared for the first part, and this one will give us t on c squared minus 2. Remember, the covariance between two dependent time processes will give us the minimum of the two times, and as we can see clearly, t plus s is greater than t, so of course t plus s on c squared as well should be greater than t on c squared. So that makes our minimum time to be t on c squared, right? Yes. From this expression, you realize that c squared is common, like 1 over c squared is common. We can bring it out, and that neutralizes this constant that we are multiplying here with. So the expression will give us I think this 2t plus s minus 2t, which will give us a final answer of s. So now we've been able to show that the stationary increment, that is nt plus s minus nt, is normally distributed with a mean of 0 and a variance of s. Right, so let's look at independence. That's the last one. So we want to see that this process nt plus s minus nt should be independent of mt, right? Yes. So by independence, so we can say that since the mean of nt and that of nt plus s minus nt are all 0, then the covariance becomes the same as the expected value of the product. So as we find the product, we're going to end up with this. And looking at this, I think this is the covariance between nt plus s and nt minus the variance of nt. Since this the first moment is 0, the variance becomes the same as the second moment, so that's the variance of nt, and this covariance becomes the minimum of the two times. So, and that minimum time is going to be t, so that gives us t minus t, and the covariance becomes 0. The covariance becomes 0. Yeah, so that means that there's independence between these two processes. It means that nt actually satisfies the independence property, the stationarity, and the initial condition being 0 at all points. Yes, so in conclusion, under normal scaling, nt can be seen as a standard Browian motion. Yeah, so we can also proceed to show that the Browian motion is also a martingale in the next slide. Great. So let's see how we can show that the Browian motion is a martingale. So we take BT given the sigma algebra, that is Fs. We know that for it to be a Browian motion or a martingale, it should be equal to Bs, right? Great. So we create and destroy within the process, that is BT. So this will be Bs plus Bt minus Bs. Remember, when you add Bs and the lot of negative Bs to go to 0, giving us the same thing. So now Bs, expected value of Bs given Fs should give us Bs as well. So all we need to worry about is this. But remember, we said this Browian motion has independent increment. So once it's independent of this, so that's going to give us expected value of bt minus bs. Okay, because it's independent of this, you don't need to bring the conditional random variable. That's the sigma algebra. So yeah, so that gives us a mean of 0 for here, because bt is expected value is 0 and bs is expected value is 0 as well. So we're only going to be left with bs. So that shows that bt is a martingale. That's the Browian motion is a martingale. Thank you so much for your time being, and we've come to the end of Browian motion and martingale. So in our next topic, we're going to look at stochastic differential equations. Thank you very much once again.